Good afternoon, everybody. Can you hear me?
Yeah.
Thank you. All right, folks, just checking on what we're supposed to be doing today, making sure that I'm on track. Okay. All right, looks like we're starting out with Introduction to Substitution Reactions. I'm hoping we'll have a little bit of time at the end of this, at least one day here for review. That'll be October 5th, I hope. All right, let's get into substitution reactions then. All right, we get started now. All right, so we are working on substitution reactions. Here we go. Okay. So we're starting out nucleophilic reactions. Let's see what that means here. When I'm talking about nucleophilic reactions, what I'm talking about is this kind of situation here where we've got a C, then attached to that we've got some sort of X group, and then we have this thing coming in, which I'm going to call a nucleophile, which is going to usually have a negative charge on it. The carbon connected to the leaving group will generally have a partial positive charge. And the word nucleophile itself means nucleo is like positive, like the nucleus, right? And then phile is loving. So something that is attracted to positive charges, and that would explain why most of these things usually have a negative charge. If they don't have a negative charge, they'll sometimes have like a lone pair of electrons. So this N in ammonia is said to be nucleophilic. All right, so you'll often hear that term. The other terms you'll hear will be things like leaving group, because what's going to happen is these are substitution processes. So this would be an example. So Y minus and then CX Then the negative comes in, kicks out the X. And we end up getting Y connected to the C, and the X comes off as X minus. That's where the term substitution comes from, because the Y is substituting for the X. All right, so that's simply what it means. So if we're talking about a nucleophilic substitution, we're talking about something that's usually got a negative charge coming in and displacing or substituting for something else that's already attached to a carbon atom. So that's the very basics of what we're doing here. Now we're going to be dealing with two specific nucleophilic substitution reactions. The first one will be in Sn2, the second one will be in Sn1. Now I'm just going to go through here very briefly and just go through some of the nomenclature that we talk about. The basic form of any substitution process involves something R bonded to X, where R is anything. Don't worry about what the R is. Usually it's something containing carbon. And then Y minus comes in, replaces the X, and the X leaves as X minus. So the X substitutes for the Y. Y is called the nucleophile, and X is called the leaving group because it's leaving. Now, in the case of the nature of the leaving group, the best leaving groups are the ones that are stable as negatively charged compounds. Things like Cl negative, Br negative, I minus, RCOO minus, which is really this. That's fairly stable as a negative charge because it can resonate. If you'll remember, we talk about resonance. Now the other one, TSO minus, this is a really good leaving group. It looks like this. It's got a benzene ring in it. Toluene sulfonate is what it stands for. And you can see all the resonance possibilities that would exist for this negative charge as well, which is why this is going to be a good leaving group as well. So anything that's stable as a negative charge is a good leaving group. The other thing that's a good leaving group are neutral stable compounds like water or alcohols. Those are also good leaving groups as well. So we're going to be talking about the Sn1 Sn2 processes. Let's look at a couple of videos here, and I'm going to go back to here, and I'm going to steal one of my videos that I've stolen from somebody else.
I have a quick question,
Oh,
Professor.
yes, Jonathan.
All right, so the stable compounds are the better leaving groups because they exist by themselves better.
Yes,
is that correct?
That's exactly right. Yeah.
Okay, thank you.
Yeah, so things like Cl minus makes a good leaving group because Cl minus is really stable on its own. Yeah, same with water and alcohols as well. You'll see an example of how we get those. It's usually by some sort of catalytic process, and you'll see that in a second. All right, let's see. I've got to find the right.
Is Cl not a diatomic molecule? I would have thought it would not be stable by itself.
Well, Cl negative is stable. Cl by itself, not so much.
Mm-hmm.
Right, because that doesn't have a charge on it. But remember, Cl has 7 electrons in its outer shell. If it gets one more, it becomes negative. Then it becomes and it's fine. But
that makes sense.
But you're right. Cl without the charges is not stable at all, which is why it does form that diatomic molecule, generally speaking. But that's the difference between chlorine and chloride, right? Chlorine, chloride. Okay, let's have a look. Let's see if we can. If I have this. No, I'm actually going to not do this. I don't know where the link is. I had this other link. I'm going to go to another. Can go to another thing here. All right, let's have a look. Okay, let's see. You can see what I've been working on. All right, let me see. Sorry, Sn1. Yeah, here we go. Let's do that. Okay. So this is a really cool. We'll do Sn2 first. This is a really cool thing here. Hang on. Oops, stop. I need to share this properly. Oops, wrong one. You don't want to see my VPN. Let's go back. Here, no, still doing that, sorry. Here we go. New share. There we go, share computer sound. Okay, that's what we want to do.
Halogenoalkanes undergo
Okay. That is a short video.
Primary halogenoalkanes undergo Sn2 reactions, where the S denotes a substitution reaction.
I like how they use the echo here. Yeah, it's really cool.
The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step.
Now, an Sn2 reaction actually only has one step, and it involves 2 species, and you'll see that when we look at it.
A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom. Because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile.
Sorry,
the lone electron on the
having some trouble. Hang on.
nucleophile forms a new dative covalent bond
Come
with
on.
the partially charged carbon atom to give an unstable transition
All right. Can you all hear me?
complex.
I'm having some trouble with this.
The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion called
Yeah,
the
give me a
Is
second.
anyone
Yeah.
else is still
Mine's
like
worse.
freezing
Yeah, I
up?
am.
Sorry. I'm not sure why.
complex.
Sorry about that, folks. Can you hear me?
Yes,
Barely.
we can hear you.
Yeah. Look, I'm really sorry. I'm having some sort of technical issue with this, and it's kind of screwing up everything at this end. It just crashed, so now my internet connection's not very stable right now. So just give me a second, and I'll get it sorted out.
Am I able to ask you a question while you do that?
Yeah, you can ask me a question, sure. Hopefully, I can hear you. What's up,
So-
Jonathan?
From the video, what I think it was trying to show is that I think it was bromoethane could only attack the hydroxide molecule from that certain side because of the size of the bromine atom on the
Right,
other side of it. So
yeah.
it had to attack on the side with the 2 hydrogens. Is that
That's
what it was
right.
showing?
Yeah, that's what I was trying to show. Yeah, I'm
So-
sorry about that. Yeah, go on.
Would it displace, or I guess substitute one of the hydrogens for that molecule then?
No, it wouldn't substitute. No, it would only replace the bromine. The hydrogens move, but they don't go anywhere. I mean, they change position, but they don't actually leave the molecule.
So the electron goes to the bromine, and then the electron pair from the hydroxide goes to the carbon.
Right.
Okay.
Now listen, I need to, I think I need to leave this connection for a second, then I'm going to come back. No, I don't want to leave the meeting here. Let me see if I can get this sorted out. All right. Okay, I think things might have stabilized now. Have they stabilized? Can everybody hear me now?
Yes.
Okay, good.
Yes.
All right, good. All right, so it looks like everything might have stabilized. We might be able to manage to do this again here. Yeah, okay. Let's go back to YouTube. We'll try this again. I thought I had links to this in the thing. I think I do, but I'll if I don't, I'll see if I can manage it.
I think you do. I think I might have seen it before.
Yeah. Here we go.
Consider the reaction between a hydroxide ion solution and bromide. Both reactants are involved in determining the rate of the reaction.
I don't think we see your screen.
You don't think we see a screen? Okay. No, probably because I unshared it earlier. All right, let's go back.
Yep.
Let's try that. Okay, sorry about that. Okay, now I'm screen sharing. All right, thank you.
Side ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable.
All right, so hopefully you can see this. Can you all see this on the screen?
Yes.
Okay, so what we're looking at is what's called the transition state. And if you look at the energy diagram, you see it's the very top, because at this point, this carbon has 5 things connected to it. Now, they're not, it's not a very stable situation. So it's there for a very, very small amount of time, then it's gone. In fact, one might say an infinitesimal amount of time, because it doesn't want to stay in this position. So that's why you get this, as it's approaching, let's go back a little bit here. You can see as it's approaching,
A hydroxide ion, and B, it repels the negative charge nucleophile.
so you can see as it's approaching, the energy goes up, because you're joining this together and you're forming this thing that has 5 bonds on it.
The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released.
Right, so as you can see, once this breaks apart, then the energy comes back down again. In this case, the products are actually of lower energy than the reactants. That's called enthalpy, that difference between the reactants and products. And because it's lower, we know that this must be an exothermic process. It means this amount of heat is released. Now, endothermic would be if the reactants were above, the products were above the reactants. Let's say they were up here somewhere. But the overall shape of the energy diagram would be the same. So this is a one-step, one-hump process that involves 2 molecules, the OH minus and the thing it's reacting with. And that's why it's called Sn2, because there's 2 things involved in this slow step, which is the transition state. There's only 1 step. Okay, this is something that you're going to need to be able to do, is draw these energy diagrams. This EA here represents what's called the activation energy. And it's the energy needed to make the two things actually join together to form this transition state that they talk about.
Behaves like an umbrella blowing inside out as the bonds.
And so there you go, that's the transition state right there. As you can see, the overall shape of it is a trigonal bipyramidal. You know, if you've got 5 things around a central element and you want to have as much space between them as possible, it's going to take on this shape of a trigonal bipyramid. You see it's got 2 triangle pyramids joined at their bases is the way that you look at it. And that's usually what we talk about when we've got 5 things attached to a central element. Okay, does anybody have any questions about what they're seeing with the Sn2?
Yeah, so in that image right there,
Yes.
why is it in every situation that the bromine is, or the bromide ion, the one that leaves,
Mm-hmm.
it's not gonna pick the hydroxide, it's just always the bromide?
Oh, well, I mean, at this point, at this very step here, there's 2
Yeah.
directions. I mean, think about rolling a ball up a hill, Jonathan.
Mhm.
If you don't put enough energy in, what's going to happen if you don't put enough energy into the ball?
It'll roll back down.
It'll roll back down, right? So
Mhm.
think about it. At this point here, there's 2 directions it could go. The bromide could leave or the hydroxide could leave.
Right.
If the hydroxide leaves, then it just goes back to being reactants. It's kind of like not having quite enough oomph to get that reaction to go.
Okay, so it would go back and then it would get the energy again and attempt the same reaction all
It
over
would.
again.
That's exactly right. Until it got enough energy to make that happen. Yeah,
Sure.
sure.
Interesting.
All right. Any other questions about the Sn2?
Dr. Musgrave,
Yes.
does the bromide make the complex necessarily unstable, and that's why it leaves?
Well, it's more the fact that there's 5 things connected to that carbon that makes it unstable, because carbon really wants to have 4 things attached to it. It's a very unstable situation. But you're right in that the bigger that leaving group is, the more unstable it should be.
Okay, thank you.
Right. So iodine is even more effective as a leaving group because it's bigger, and it would destabilize that situation even more. So from that point of view, yeah, I'd say I would agree with you. So let's look at the Sn1. Now this is a little bit different, just a little bit.
Tertiary halogenoalkanes undergo Sn1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups.
Right, so now this is what the previous one was called a primary because it had hydrogens here. Now these are methyl groups, and this changes the way that the compound reacts and the way that the substitution reaction occurs.
Tertiary halogenoalkane. The bulky alkyl groups do not allow attacking species to approach the central carbon atom.
So you can see here that nothing can jump in from the back here and kick this group out like we saw in the previous one. So it has to happen a different way.
Consider the reaction between 2-methyl 2-bromopropane and a hydroxide ion. It has a 2-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction.
All right, so the first step here, the bromine just leaves by itself. Now, I mean, you might be saying, well, come on, I mean, how does it just do it by itself? Well, the thing is, if you've got a bottle of this stuff here, this 2-methyl 2-bromopropane, then a small percentage of it is always dissociating and then coming back together again. So there's always a small amount of this always going back and forth on its own. And then what happens, you see what happens next.
The first step involves only the halogenoalkane and proceeds via a transition state complex.
All right, so that bromine comes off as Br minus. We're left with a C plus, and this is called a carbocation. It's a carbon with a plus on it. That's why it's called a carbocation. And you'll see a better picture of this in a
To
second.
form a carbocation.
There you go. See, it's flat. The C has a plus on it.
The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step.
The reason that that second step is so much faster is because you've got something negative reacting with something positive. If you go back to the first step, what happens, it'll show you in a second, but what's going to happen is you're taking something neutral and turning it into something positive and negative. And that's always more difficult than taking a plus and negative and putting them together.
The carbocation reacts with the nucleophilic hydroxide ion via a second transition state to form the product 2-methyl propan 2-ol.
Anyway, watch this here. This is kind of cool.
Transition state, carbocation.
Let's go back. That transition state, let me show you what's happening on the transition state. The transition state, that bromine is in the process of leaving.
Transition.
Okay, that's the transition state. It's kind of, at that point, it's at the cusp. It could either stay or go at that point. If it stayed, it would go back down to the reactants. But if it goes, then it goes on to the next step.
State, carbocation, EA2.
I do have a bit of a complaint here at this point. Really, this is the transition state. Can you see my cursor? Can we see the arrow here?
Yes.
Okay.
Yes.
So at the top of this hump, the C and the O should actually be at the cusp of joining together. So I think they got it wrong here. They join it down the track here, but it really should have been just about to join at this point, at the cusp of joining or not joining. See, they join it at the bottom. It really should have been joined way back at the transition state.
Sn1 Reactions.
All right, so there you go. Does anybody have any questions about I do have the links to that somewhere in the mini lectures, I think. Julie, you said you'd seen it, right?
I think it was Sierra. Sorry, yes, I'm pretty sure I saw it already.
Yeah, me too.
There's a question in the chat box for you, Dr. Musgrave.
Oh, okay, let's have a look. Let's have a look at the chat. Okay. Are these pressurized gases? No, these are solutions. Yeah. No, these are solutions generally, and I'll show you some examples of solutions and how that might affect how these reactions go. All right, so those are good videos to watch. I would watch them again and again. I'm going to show you something else here that's kind of cool, but unfortunately something went wrong with my browser here and everything crashed and it was awful. All right.
So does only Sn1 have the carbocation?
Yes, Sn2 doesn't, because it
happens at the same time.
happens all at the same time. It's exactly right.
And there aren't any other reactions with the carbocation.
Well, there's lots of reactions that involve carbocations, but we're only talking about Sn1, Sn2 here.
Mm-hmm.
And you've got the one-step process, you've got two-step process. I'm about to explain why you have that difference, but it has to do with the structure of those molecules and why that happens. All right, let's see. Let's go down. Actually, I think it's in the Sn1 Sn2 folder. There, this is it. This is where those links are. So I put them in the Sn1 Sn2 folder, but I wanted to show you this as well. I like this little diagram here. Yeah, some people are just nerds, aren't they? Look at that. Okay, so what's the top one represent? The top one represents Sn1. So you've got this little cat sitting in his bed, right? But he leaves of his own accord, and then the other cat comes in and just sits in the bed. But look at the look on this guy's face here. He's not very happy about that. But look at the Sn2. You see, what he actually has to physically do is push the other cat out of its bed. He's still not happy. But you can see the difference there. Right?
So Sn2 is going to require more energy than Sn1.
Not necessarily. I actually can't make that statement, Sierra. There's a structural difference that occurs here. I know it may look like it from something like this, but in reality, there's a lot of other moving parts to it than to be able to make that statement.
Okay, I got you. I was just thinking like two atoms coming together would require more than breaking apart one. If that makes sense.
But see, when you have to break them apart, you have to form a positive and negatively charged species. And that in and of itself takes a lot of energy. So it's kind of a balancing thing that goes on there. Yeah, I get what you're saying though. All right, let's look at why we have this difference in reactions and what's going on. So first of all, let's talk about what we mean by primary, secondary, and tertiary. So something that's primary means that the X group or the leaving group is on the end of a chain molecule. And you can see that there'd be two hydrogens connected to that C. But as a line structure, it's very easy to look at it and say, oh yeah, that's definitely primary because it's on the end. So think of primary as being on the end. A secondary means it's in the middle. You can say like second carbon, right? Secondary. Tertiary means there's 3 carbons connected to the C with the X. And it kind of looks like a T. And you might remember some of these names we talked about back in test 1, you know, sec-butyl, T-butyl. They're kind of based around this concept of primary and secondary and tertiary. Does anybody have any questions so far?
Yeah, I have a question.
Yeah.
How come we haven't talked about secondary at all in the reactions?
Because secondary can go either way.
Okay.
And you'll see why in a second, Julie. So we take a look at the primary carbocation, secondary and tertiary carbocation. So we talked about the plus being on the C, and what we know is that out of these, I don't know why this is, I think it's got something to do with the fact I'm on a Mac, but this diagram should be a little bit bigger than what it is. I don't know why it isn't any bigger, but see if I can make it any bigger. Not really. All right, that's a little bit better. All right, so what we know about carbocation stability is that tertiary is the most stable, secondary is the second most stable, and primary is the least stable. And the reason that tertiary is the most stable is because of a concept known as hyperconjugation. And what's happening with the tertiary is that it has these CH bonds that are adjacent to the C+, and those CH bonds contain electrons, and those electrons can help stabilize the positive charge on that carbon atom. So what that means is that any C that has 3 Cs connected to it tends to have be more stable as a C+ than a C, for example, that only has 1 C connected to it. Does anybody have any questions?
Do we really have to understand why that is?
Well, I mean, the reason has to do with exactly what I just said. I mean, if you look at this hydrogen bonded to the C+ here, you can see that there's no bonds coming off it that could stabilize that positive charge. But if you've got a CH connected next to the C+, you can see that those electrons, because they're negative, could stabilize the plus next to it. That's all I'm trying to say. Is that all right?
I guess.
Can you ask a question that would help or not?
Well, I guess,
So I have a question. Are the negatives coming from so like the CH2, it's the electrons coming off of that carbon, which is going to stabilize the positive on the central carbon.
That's right. Well, because there's electrons in that CH bond, Sierra.
Correct.
Yeah.
I got you.
So Julie, did you want to say something? I'm sorry.
no, that's okay. I guess I really don't understand why the carbon is a positive to begin with.
Oh, because I'm saying it is. But if it was positive, it was because there was something connected to it that took both the electrons with it, like a Br, for example, came off as Br negative, leaving that as being a positive charge.
And why do the other C's have extra negatives? Because they're not a negative, they're a positive, they're a stable.
Well, they don't have extra negatives, no, but what they do have is they do have electrons in the CH bonds, and those electrons are negatively charged. And those
Aren't they
electrons,
used up? I mean, aren't they used up in bonds with the,
yes, but an electron intrinsically is negatively charged, right?
right?
But yeah, you're right, everything's used up in a bond, but that doesn't mean that those electrons lose their charge. They still have that negative charge, even while they're in that bond.
All right. I'll believe you.
Okay. So if we look at Sn2 reactions, the mechanism involves something negative coming in and kicking out something positive at the same time. And you can see that those arrows are going to tell the story of what's going on there. Now this arrow that I'm pointing to is Cn- going towards this C that's got the Br connected to it. This arrow is telling me the story of bond formation. Let me draw that for you a little bit. I'll try this.
Okay, I have a question here though.
Yeah.
Why does one arrow point towards the C, coming from the Cn-, and the other arrow seems to come from the bond and just points elsewhere?
Right, I'm just about to explain that. Okay, so this first arrow is telling a story of bond formation. So that's what this arrow is doing. We're forming a bond between the Y and the C. Now, how are we doing that? Well, we're using, this arrow represents 2 electrons moving. And it's going to be 2 electrons that form a bond. So in that bond, that's what we have is 2 electrons. Now, at the same time, the electrons in this bond are leaving that bond, and that becomes X negative. So you can see that that was bond breaking. So this is bond forming. And this is bond breaking.
So you need to break a bond in order to form a new one, correct?
If it's happening at the same time, Sierra.
Okay.
Yeah, that's right. I mean, if it's happening at the same time, yeah, if you're forming one, the other one has to be breaking. Otherwise, what you'd be doing then is, if you didn't have that second step, then what you'd be saying is that the Cn was joining on, but the Br wasn't leaving, which would leave that carbon with 5 bonds, which is not something that's very desirable here.
Yeah, that can't happen really.
But the fact that these 2 arrows are in the same step at the same time means this is all occurring at the same time. And that's really the key. So
Well, and that's how you can tell if it's Sn2 or Sn1?
Yes, because if it's simultaneous, it's Sn2. So it happens simultaneously. And you know, because you got the arrow here, the first arrow that's forming the bond, and the arrow here where it's breaking. So Julie, does that explain what I'm talking about with that arrow, what it's showing? The fact that the tail comes from the bond means that the electrons are coming from the bond and going on to the X. That's the story that arrow is telling. So, you know, we've got two competing stories here. We've got a story of love, a story of connection, but then we've also got a story of heartbreak. And it's all happening at the same time. Think of Sn2 as being kind of like a monogamous type situation. You know, so somebody who engages in serial monogamy, they can't have more than one partner at the same time. Think of it like that. Before they attach to somebody else, they have to get rid of whatever they're attached to first. That's what Sn2 is like. All right, anybody any questions? So with regard to the Sn2, the reason it happens is because there's enough room around this atom, because it's got the hydrogens here, for the Cn- to come in and the Br to leave at the same time. So plenty of room for concerted. Concerted means at the same time or simultaneous attack. Think of a concert. You know, all the musicians are playing something like music at the same time, hopefully. What can't happen with the Sn2 is the bromine can't leave and form a C+, because this carbocation, the primary one, is unstable. So it can't go the route that the Sn1 reaction goes. It can only go the route the Sn2 reaction goes. So let's take a look at the Sn1. So you'll notice that this was primary. This one here is tertiary. So you've got the bromine here connected to a C that's got 3 C's around it. So what has to happen here is the bromine comes off first, and you can see that arrow again. The arrow comes from the bond and goes on to the Br. And that leaves this positively charged species where the Cn- comes in and forms the product. And if the first step here is the higher energy slow step, and this is the faster step where the Cn- comes in and attacks that C+. So this can't happen as an Sn2 because there's not enough room for the Cn- to come in and attack that Br, because the methyl groups here are just too bulky. In the previous example, these hydrogens are a lot smaller, so the Cn- can sneak in and kick that out at the same time, whereas the Cn- can't do that here. But what it does do is it does form this carbocation that's tertiary, and the tertiary ones are stable. So there's kind of two competing things occurring here that, well, they're not really competing. They lead to a situation where this can be favorable for Sn1 but not for Sn2, and Sn2 is favorable for Sn2 but not for Sn1. So to answer your earlier question, Julie, what does secondary do? Well, secondary could go either way. So the other thing I can talk about here, just briefly, I'm not going to spend a lot of time on this. If the solvent, because somebody was asking about whether these are in gas phase or liquid phase, well, these are happening in solution. So if the solvent is not particularly polar, in the case of an Sn2, it can sort of supercharge the negative on the Cn because there's no stabilization of the solvent with the negative charge to help negate or make that negative charge less. So, so non-polar solvents will tend to help Sn2 reactions, whereas polar solvents, which can stabilize the carbocation or help stabilize the carbocation, will tend to help Sn1 reactions. So if you had a secondary and you used a polar solvent, maybe that could force it more in the Sn1 direction. If you used a non-polar solvent, maybe it would force it in the Sn2 direction. Not really something you have to be that aware of, but I just thought I'd point that out. So this is well, I'll show you the summary. This is the summary of the Sn1 Sn2 reactions. I'll come back to this in a bit. So the Sn2 reactions are one step concerted. The Sn2s are one step concerted. The Sn1s are two steps, or what I call stepwise. Sn2 reactions are favored for strong nucleophiles. For Sn1, the nucleophile strength is not very important. And the reason for that is because the fast step involves the negative coming in, and whether that negative is strong or weak doesn't really matter because the carbocation itself is already positive, so it will react with pretty much anything negative. So the nucleophile strength doesn't really matter so much for Sn1, but does matter for Sn2. You'll see that later on there's going to be a difference in the way that we handle stereochemistry. For Sn2, you get this inversion of configuration, which means R becomes S or S becomes R. In the case of Sn1, you get a racemate or racemic products, which means you get a mixture of R and S. I'll explain all that later. Sn2 reactions happen with primary halides, whereas Sn1 happens with tertiary halides. Sn2 reactions tend to be second order. That means they involve two molecules at the slow step, whereas Sn1 is first order, involves one molecule in the slow step. Sn2 reactions have no intermediate because they're happening at the same time. And Sn1 has a carbocation intermediate because it happens in two steps. And Sn2 is favored for aprotic or non-polar solvents, whereas Sn1 is for protic solvents. All right, does anybody have any questions just about the summary there? All right, let's look at the energy diagrams because this is what you'll have to do on the test. So the Sn2 energy diagram is always a single hump process because it's just one thing reacting with one other thing and it's all happening at the same time. The EA is the activation energy. I've got two examples here, one where this is an exothermic and the other one where it's an endothermic. You can see the difference between them is that for the exothermic, the products are below the reactants, and for the endothermic, the products are above the reactants on the energy diagram. So we have energy on the y-axis in each instance. Let's take a look at why that might be. So this is for anything really. So I'll put energy here. So this is reactants and this is products. The delta H is always just this energy right here. The difference between the reactants and products. It doesn't matter what's going on with this hump, whether it's a 2 hump, 3 hump, 4 hump, whatever. It's always just the reactants and products. That's your delta H. Now, if you go back to what delta H is, delta H, if you remember, this is from way back in General Chemistry 1 or 2, is the sum of the heats of formations of the products minus the sum of the heats of formations of the reactants. Do you remember that from way back? So let's just think of it as being products and reactants. So if delta H is essentially P minus R, and you've got a small number minus a bigger number, then you're going to get a negative value, which is essentially an energy release, which means it's exothermic. And the reverse case would be where the products are above the reactants. And in this instance, then you've got a big number minus a smaller number, which is, of course, is going to be positive. And that's going to mean energy's been taken in, and that's going to be endothermic. But the bottom line here is just where the products are in relation to the reactants will tell you whether it's endothermic or exothermic. Does anybody have any questions?
So where would the delta H be on this diagram?
Oh, on the second one? I
Yeah.
probably should, I should have put that in. Sorry about that. Here he is, right here. Still
Okay.
between the products and the reactants, right? Now they both have an activation energy as well, but that's always from the reactants to the top of the peak. And this one also has an EA as well, right here.
So it's okay if the EA and the delta H overlap?
Absolutely, because they're showing two completely different things occurring. The EA is what it says it is, the activation energy, the energy required to make the reaction go, the energy required to get to the top of the hump. So it's just imagine it as being rolling a ball up a hill, having put enough energy in to make that happen, you know, get to the top of the hill and come back down. All right, so that's just to give you the lay of the land there with the EA and the delta H. And you can see that the EA and the delta H is still going to be the same kind of thing, even in the case of an Sn1. But look at the difference in the energy profiles. The Sn2 is a single hump process, and the Sn1 is a double hump process because it's 2 steps. The activation energies on an Sn1 look like this. I'm just going to do this is an exothermic because that would be the reactants and this will be the products. And there's your EA again, at least for the first step. And then there's actually an EA on the second step as well, but you can see it's a lot smaller. So we've got EA1 and EA2, but the reaction, if it can get over, here's the thing, if it can get over EA1, then it can definitely get over EA2. So the only step that really matters is for how fast the reaction's going is going to be EA1. And we call that the rate determining step. So the first step is what we call the rate determining step because it determines the rate. It determines how fast the reaction goes. You can think of it this way. If you've got like a sand in an hourglass here, but there's a really skinny neck at the top of the hourglass, it doesn't matter if that's the skinniest neck, then that's one that's going to determine the rate. These can be as wide, these large openings can be as wide as you want, and it doesn't really affect the rate at all. All that affects the rate is the narrow opening at the top here.
I have a question, Professor.
Yeah. Mm-hmm.
So is the rate determining step always the first step, or is it always the one with the highest activation energy?
It's always the one with the highest activation energy, but for our purposes, it will always be the first step.
Okay.
And the reason for that, again, goes back to the mechanism here. The first step involves the formation of something negative and something positive, which is always a high energy type situation. Taking a bond and splitting it into positive and negative is very high energy. Let me clarify that a little bit here. So if you have two things, X and Y, and you split them apart into X plus and Y minus, that takes a lot of energy. But if you have an X plus joining with a Y minus, That's a very favorable process. So that's a low energy process, which explains why these two humps here are so different in size with regard to the activation energies. So the first hump is fairly large, whereas the second hump always has a fairly small one. The activation energy is from the transition state, which is the well here, the energy well, up to the top on that second step. So it's very tiny because it's the plus joining to a minus. All right, any questions?
The second hump requires less energy because it's kind of like a residual from the initial energy, right, to get over the hump?
Well, if you've already got enough energy to get over the first hump, then you've definitely got enough energy to get over the second hump.
Okay.
Yeah, you think of it like a skier going down a hill. I mean, and the skier, let's see if
No, I understood.
Okay, fair enough. Okay. All right. Any other questions at this point? All right, and let's go take a look at the test question, because I think that's really what you want to know about. Now, there's really 4 possibilities for the test question. Just 4. That's it. And I've got them all laid out as well here and in other places. I've got them laid out in the videos as well. So consider the exothermic nucleophilic substitution reaction below. For some reason, the yes, it's not really coming up the way it should. But anyway, I'll redraw it. It's not very much fun, is it? Okay. But what it is, in the question is this. All right, so that's what you're given. Let me shrink this back to what it was. Okay, is the reaction forming the major product Sn1 or Sn2? Does anybody know? Sn1 or Sn2?
Sn1.
Okay, why would you be saying that, Deanna?
Wait. Because it's a primary structure, right?
Okay, so primary, if it's primary, which way is it going to go? Let's go back and take a look. See, primaries go Sn2 and tertiaries go Sn1. So it's really that simple. So
Well, if we learned Sn2 before Sn1, it's kind of confusing.
yeah, but Sn2 is only involves, no, it's one step. That's what I think. I think it's fine, Julie.
I think it's fine too. I just got confused.
So primary is Sn2. If it was tertiary, tertiary would be Sn1.
I'm sorry, maybe I missed it, but did we discuss what happens with secondary?
Secondary could go either way.
Okay.
Yeah, so you won't have any questions. I promise you this, Jonathan. You have my word. May lightning strike me down. May lightning strike me down. You will not get a secondary on the test.
Or quaternary?
No, not that either.
Okay.
It'll be primary or tertiary. So if it's primary, it'll go Sn2. Tertiary, it'll go Sn1.
Deal.
All right. Okay, so we know from the question whether it's going to be Sn1 or Sn2. The next thing we need to do is draw an energy diagram. And this one here, it says in the question, it says exothermic nucleophilic substitution. Exothermic is the key here. So when I'm drawing the diagram for an exothermic, what I have to be sure of I draw the energy here. I'll put reaction coordinate or reaction pathway or something like that down here. You can do either, doesn't really matter. But if it's exothermic, I have to draw the product up here and the reactants down below. All right, that would be exothermic. Is everybody okay with that?
No.
Okay, Francisco. So what I was saying earlier was that when the delta H has the products below the reactants, that's exothermic. It means that energy has been released during that. Exo meaning out, thermo meaning heat, so heat out. So when the products are below the reactants, it's always going to be exothermic. If you put the products above the reactants, that means endothermic. Is that okay?
I'm actually confused too.
So the graph here is different, right, Jonathan? The graph.
Yeah,
that
yeah.
notes.
So you said when it's small minus big, it's going to be negative and it's exothermic, right? And the equation is P minus R,
Yes.
where R is the first and P is the last, right?
Yes. Mm-hmm.
And so if you put P above R, then it should come out as positive.
It will, that's right.
And if you put R above P, it's going to come out negative.
Yes, that's true.
Could you go back? I just want to double check what you drew.
I think, well, let's hope I did. Oh, sorry. I put these, all right. Okay. I mixed up the R and the P. All right. Fair enough. All right. Sorry.
Nice catch.
Yeah, all right. Okay. All right. You got me. All right. So the reactants go above the products. Now, if it's an Sn2, it means it's a single hump. The delta H will still be between the products and the reactants, like this. And the activation energy will be from the reactants up to the hump. So that's the EA right there. All right, any questions? So that's how you would draw the energy diagram. So we showed the delta H and the EA, I've already done that. So the delta H is between the reactants and products, the EA from the reactants up to the hump. And then it's asking for the transition state. Now this is probably the worst thing to have to draw on the question itself. And the transition state is showing pretty much what we saw in the videos. We see the Cn and the Br at the cusp. That's why we've got these dotted lines here. These are partial bonds. All right, let me draw this for you over here.
I have a question.
Yeah.
Is that the stage right before the Cn leaves?
Yes.
Okay.
No, well, before, no, the Br leaves.
Okay, the
Deanna.
Okay.
Yeah. So let's look at how we're drawing that transition state. You'll notice I'm drawing it in 3 dimensions. And I'm trying to show you here the C's. So there's the C's in the initial compound. And there's the C there, C, C, and C. So those are the 4 C's.
Why did you change the shape of it?
Well, because it looks prettier for me to be able to draw it.
What if we don't change the shape? Is that okay?
Well, as long as you show but you still have to show the stereochemistry here. So as long as you can still show that stereochemistry, that's fine. But that's what the transition state looks like. You'll notice that it's in that trigonal bipyramidal shape. couple of things about it. That's 180 degrees right there. And this is 120. So it's really the only way you can draw it. I mean, you could draw it, well, I don't know. Okay, we can draw it another way, Julie. I mean, if you really don't like that. Let me see if I can do it. Let me put it on another place here. I'll put it down the bottom here. Just need enough room. Do you like this more? Maybe you like this more.
I already like it more.
You do? Okay. Well, then that's a beautiful thing, isn't it? Okay, so that's the same thing. Now, this funky cross thing here is the universal symbol for a transition state. And generally speaking, we put a transition state in square brackets. We put this funky cross thing on the outside to say it's a transition state. A couple of other things. The dashed line here to the H represents stereochemistry. That's the bond. That's the bond going into the page. That's what that's indicating. The dots here indicate partial bonds. Bonds that are forming or in the process of forming or breaking. So we'll call them partial bonds. But they're dots, they're not dashes.
Why are we putting the H's in on this one and we don't put the H's in on the other end?
Where are you talking about, Julie? Which end?
Well, you're putting the H's in here because there's 4 bonds on that C, and you're putting the CN, the BR, and the 2 H's in there.
Yes, that's right.
But the other side, the last C, would have 2 H's too, wouldn't it?
Well, this C here would have 3, this C would have 2, this would have 2, and this would have 2. But the reaction center is where the bromine is. So we're not interested in what's going on the other carbons.
Okay.
But I have to draw it this way so that I can get an impression of all the bond angles. So that's what makes the SN2 a little bit of a bear to draw. Does anybody have any questions about drawing that transition state?
Are we able to go through one more?
I'll show you. Let's see if we have time. I'll do another example. But let's look at the SN1. See how much time we've got left. Okay.
Just a quick question.
Oh
Is
no,
that
actually,
symbol-
I wasn't done with this. I'm sorry. What's that?
That's okay. I can see it now on the slide. The symbol, it's just basically a double crossed line.
Yeah, that's right.
Is the bottom line supposed to be shorter than the top line?
Yeah, it is. Yeah, it's supposed to look like this.
Thank you.
Yeah. I guess more like an Eastern Orthodox cross.
I see that. Okay, thank you.
Okay. There's one other thing we had to do here, draw the mechanism for the reaction. Now the mechanism is what involves the arrows. And I think that's what sometimes happens too, is that people get the mechanism and the transition state mixed up. So the mechanism is going to look like this. Now, if you don't know that the negative's on the C, that's okay. I'll understand that. But on a CN negative, that's where the negative charge resides. And in the arrows, with the arrows, you're telling that story about the CN coming in and the BR leaving simultaneously. So that's the difference. That's the mechanism, and these are transition states. TS. TS. And either one of those is fine. Does anybody have any questions, especially about the difference between a mechanism and a transition state?
I just have a quick question on the mechanism part. Why did you draw the CN up instead of down?
I could have drawn it down. It's just that it kind of looked like what it was doing, how it was coming in from the top and kicking out the bromine from the other side.
Okay, got it.
But no, I didn't have to do it that way. Okay, let's take a look at the next one. Now, the next one, again, the diagram isn't coming up here. And I think it's SH minus, or no, it's CN minus, it's CN minus. It's SH, but it wasn't. Okay, so CN minus. Now, often it's represented with the negative on the N, but really the negative's on the C. So the first thing we know is that because it's tertiary, that it's going SN1. And if it's SN1, and this one particular one is exothermic, then what's going to happen is that the products have to be below the reactants, and it has to be a 2 hump where the first hump is much bigger than the second hump. So it really does have to look this way. So we'll have our reactants, we'll have our products. It's exothermic, that's why I've put the reactants above the products and products below the reactants. And there's my energy diagram for the SN1. So it's SN1, which is tertiary. The energy will be over here on this axis, reaction pathway on the bottom. And then the delta H will be between the reactants and products. And then the activation energy will be from the reactants up to that first peak, because that's the bigger peak. So that answers A through C. And then we need to draw the transition states. Now the transition states, there's going to be 2 of them. There's going to be one I'm going to call TS1. And this one I'm going to call TS2. Now I'm going to actually show the mechanism here, because the mechanism can actually help us with the transition states. So I'll do the mechanism before the transition states here. So the mechanism is going to go something like this. So the Br comes off first and gives us the positively charged species and the Br negative. And then the Cn minus comes in and gives us our product. So it's a 2-step process, which is why we end up having 2 humps. But if you look at what's going on in the first step, is that the bromine is coming off, and that's what the transition state is going to look like. So this, again, is a partial bond. That's not a stereochemistry line, it's a partial bond. So that's for TS1. Now TS2 look what's going on. The Cn is joining to that C plus. So then we'll have this situation for the nucleophile coming in. And again, that's a partial bond as well. So there's your transition states. And again, look at the difference between a mechanism and a transition state. Yeah, I'm sorry, Jonathan, it doesn't look like we're going to have time to do another example. I'm hoping that on the review day, we'll get a chance to do some of those, but I have the old tests, obviously, but there's going to be, I think, some other worksheet examples as well that are helpful for this too.
Can I ask one question about this?
Yeah.
How come in the last one you had stereochemistry and you had hydrogens coming off forward and backward, and here you don't have any of that?
Because it's not necessary. The transition state for the other one was really dependent on the shape of everything and having the 5 bonds there and showing everything that was going on. Whereas for this one, more of what's important is where the partial bonds are forming, but not so much the stereochemistry.
Okay.
All right, we'll leave it there for today, and we'll continue on Monday.
Thank you.
All right, I'll see you all later.
Thank you.
Thank you.
Sierra, Natalie, do you need anything?